Hello, my name's Dustin Kirkland. I'm a product manager at Google, and I'm joined by two of my colleagues, Andrew Jackson, a software engineer at Google, and Josh Hoke, also a software engineer at Google. They are going to tell us about a pretty exciting model being trained on top of Kubernetes, and they're currently training another Go AI, a game, an AI that's learning to play the game Go. All right, give us a little bit about this project and how it got started.
Sure. Okay. So Deepmind is a different alphabet company based in London, and they're mostly a research-focused company that wrote this paper that was published in Nature about mastering the game of Go using tree search and deep neural networks. And this was sort of a revelation because beating professional Go players has been a long-standing goal in artificial intelligence. It has been a long time in coming, whereas Deep Blue was, 30 years ago? Was it 30 years ago?
Close to 90s.
Long time, yeah, long time, 20, 30 years ago. Go has seemed a really long way away. And then out of nowhere, DeepMind's like, oh, by the way, we did that. And they published this paper, and it was kind of a revelation. And then later the next year, I think they played world champion Lee Sedol in Seoul. They published another paper where they said that they didn't just train a network to beat a professional Go player, they actually trained it with no human input whatsoever, that it started from essentially random noise and learned how to play by itself. So
What's crazy is that this Go AI was better.
Was better than the first one.
It was
right.
fantastic.
Sorry.
That's fantastic. Okay, so that's the DeepMind team. Now this is a different group at Google that you're representing here.
We're actually not a group at Google at all. So this is not a group at Google, and this is a side project. This is an enthusiast project because
20% project.
we're Go players who love the game Go, and we really wanted to have a chance to play against AlphaGo, but of course we couldn't, so we had to sort of rewrite it. And so MiniGo is an open source ground up rewrite. I shouldn't even call it a rewrite. It's an implementation based on their published work. It shares no code. We're not related to that team at all. We have no relationship with that team whatsoever, other than the fact that we're able to implement their published papers and try and reproduce their results. So this is sort of interesting from a reproducibility of results perspective. And also that this is an open source demonstration. You know, they had built a really fast performance solution that was really baked into the Google stuff, as we assume. And so what we wanted to do is we wanted to provide an excellent example of how you could use the Google Cloud Platform and really amplify and leverage some very limited developer resources to try and achieve some really amazing results.
Okay, so this is an open source project built on your 20% time at Google, our sort of Friday afternoons where we can work on fun things related to the field. Now tie this to KubeCon. We're here at KubeCon in Copenhagen, and you guys just gave a talk?
Absolutely. So we just gave a talk because the whole way that we trained, the whole way we got data was with Kubernetes. We had this problem where we needed to create hundreds, thousands, actually millions of games in order to get the sort of strong model, right? So what did we do? We used Kubernetes. We used machine learning.
What do we do? Machine learning.
Machine learning. That's
Okay,
right.
so
It's kind of a punchline, but I think the important part here is that this is reinforcement learning, where the algorithm has to create its own data to train on, and that creation of data is a really expensive part of the overall process. So in other reinforcement learning applications like robotics, running these simulations that produce the next iteration of data is really computationally expensive, whereas for the Go domain, for the domain of playing Go, that can be very easily parallelized in a very natural way.
So the parallelization. Now you guys ran a huge model to train your implementation, and you use Kubernetes to orchestrate the playing of the games. Is that right? That's that right, more or less?
That's right. So we used Kubernetes. We actually used GKE, and we created a giant cluster. And not only
Define giant.
I think we were running, what do you say, like 2,000 nodes?
2,000 GPUs.
Right. So we were
GPU instances.
Right. So not only were we using a whole bunch of machines, we were using a whole bunch of GPUs to train our models. Right.
And this problem is particularly well suited for CUDA and GPUs, right?
Absolutely. And so the reason why it's super suited to GPUs is because we're running things through machine learning models, through neural networks. It's just math, just matrices. And the thing that GPUs are really good at is actually running things through matrices.
Okay, so each game that was simulated, 20,000 games that were simulated, each of those ran in a Kubernetes pod as a container.
That's right. And we scheduled all these pods, all with the Kubernetes batch API, the job API, and we set parallelism way up, and Kubernetes just took care of scheduling on all these machines. It was fantastic.
Now, can I Docker pull this image and, I don't know, run a game simulation for fun on my laptop? Obviously not GPU accelerated.
Absolutely. If you have a GPU accelerated version, you can do that as well. That'll be a different image, but for sure, we have these available. You can pull down the image. We actually have a UI attached to that image, so you can actually watch it play and see it think as you do that. That's actually our demo that we have.
I'd love to see that. So how long does playing a game take a simulation?
Well, just a couple minutes.
Just a couple minutes. If you don't have a GPU, it can take quite a long time.
It depends how much you want it to think. That's
right.
The real question. You want it to think a while? It could be done, if you want it to think a long time, it'd take a long time. You want it to think very quickly, won't take as long. It's your choice.
But with GPUs, maybe a couple minutes for a game.
A couple of minutes a game.
Almost all of the load is taken care of by the GPU. There's very little work that's actually done by the processor if you're using the GPU acceleration. So.
All right, fantastic. I would love to see your demo.
You got it.
Talk us through this.
All right, so what we're seeing here is what we'll see in a few seconds. I guess I should wait. All right, what we're seeing here is we're going to see Minigo think. It's going to be trying to figure out what moves will be played. So on the left side, we see the principal variation, and it just decided that it wants to play this move. So now it's going to be my turn. I'm going to play there, and then we're going to see Minigo think again. So I decided to play there, and Minigo is thinking white will play 1, then black will play 2, then white will play 3. And as those numbers move around, it's changing its mind about what it thinks is the best outcome for both sides. The other graphs that we see here, so this board up here at the top is the actual inferences that are happening on the model right now. So each of those is 1/20th of the total number of possible board positions that it's looking at. So just like how a human would play the game, where we try to think ahead and anticipate what's going to happen, and then by visualizing what will happen, we then try and decide whether or not we like where we're going. Minigo is doing exactly the same thing. It's trying to read ahead what the best choices are for either person, and essentially figure out whether it likes where the game is developing. So that's what the top one is that's each of those inferences. The middle one is all of the different moves that it's exploring. The bottom one is the change in score for a given playout. This graph that you see in the upper right-hand corner is how it thinks the game is going for each side. As it goes up, it thinks one side is winning. As it's going down, it thinks the other side is winning. And so all of that debug information is all there. So.
Yeah, and I should say, one of the key things is, of course, Minigo thinks much faster than we do.
That's
and
right.
that's why we're only sampling 1/20th
That's why we're only sampling 1/20th of its total positions.
its positions. That's right.
So as Go players, this is really interesting for us to watch and see what it's thinking of, where it sees things that we maybe don't think of, or moves that we wouldn't think of, and we can also see what it thinks the continuation is, what will happen after that. So this is a really great study tool, and it's useful for us as Go players.
And I should say, one thing that's super fascinating is I look at this game and I'm like, this is something that I would play. This is actually looks like a very human game to me.
That's right. This is a smaller model. We should mention this is a 9x9 game of Go. The real game of Go is actually 4 times as big as this, but this is a smaller version that is easier for us to run locally and essentially give a demo on a laptop instead of on a big beefy GPU machine. So this is a smaller version. It's a smaller model as well. But as a result, that doesn't really matter. We've got full-size models as well. You can download those also off of our bucket with all of our data.
Right.
So.
Are you ready to take on a human?
Yeah, we've taken on humans. This has been playing in public against anybody who wants to play it on Go servers. It's still in development, and we're hoping that we can replicate the results and then also start to explore what else can be done with it, what can be added, what other sorts of options there are. So.
But there's definitely a lot to improve.
A lot to do.
There's always bugs to figure out. We're
That's
always
right.
making it better.
If you want to find us on, this is all on GitHub right under the TensorFlow repository. So github.com/TensorFlow/Minigo. We'll take any sort of pull requests, comments, issues, complaints, conspiracy theories, whole thing.
What a fascinating project. Just tying this back to Kubernetes one last bit. So Kubernetes provided you some infrastructure underneath. Without a Kubernetes, what were your options, I guess?
So after I had finished the initial implementation of this, I realized that the hard part wasn't actually implementing the neural network. The hard part was figuring out how to do this huge amount of self-play and create the data. It's not just 20,000 games, it's 20,000 games per model, and you need to do 500 models, maybe. So it's a huge amount of this compute that I needed to figure out how was I going to do that when each game takes minutes to play. And luckily I knew a guy who worked on Kubernetes, and I was able to say, hey Josh, how should I do this? Should I script a bunch of bash to manage VMs directly?
Totally.
Should
Bash
I?
is the
Yeah.
right
Oh
option.
man, I had all of these other how am I going to get this at scale with only the open source tools, because I didn't have any of the Google infrastructure to lean on.
I guess that's the other piece, right? The infrastructure. You didn't have to provision a single VM. You didn't have to find a GPU.
I did have to do a lot of work in getting the code to work inside a Docker image, because this involved making those Docker images very performant. Docker's abstraction is, well, don't worry about what the actual silicon is underneath. But TensorFlow and GPUs, we're very much trying to compile with all of the processor optimizations. We're trying to compile with the latest NVIDIA drivers. Getting all of that to work inside the Docker image was non-trivial, but it's also gotten a lot easier. I think in particular with the launch of GPUs on GKE, that whole situation with getting the latest drivers, getting CUDA and cuDNN installed, that's all come a long way. And even when we started this, it was only, I guess, 6 months ago. It's come a long way just since then. So it's pretty exciting to see that sort of progress. But that hard part was getting that performance inside those containers. So it is interesting to see that containers are no barrier to this sort of high performance computing.
Yeah.
If you want to use GPUs and go as fast as you can, you want to use all of the extended processor instructions, you can do that too in your instances with just a little bit of care in how you craft them. So I think that's pretty interesting.
That's fantastic. Josh, Andrew, thank you for your time.
Thank you.
Yeah, thank you.